So now let's see what exactly is a support vector machine or an SVM. Given a set of training examples, each marked as belonging to one or other of the two classes or categories, an SVM training algorithm builds a model that assigns new examples to one category or other, making it a non-probabilistic binary linear classifier. So, if we have a set of training examples in which we have trained our support vector machine, so our support vector machine can mark each of the training example either to one of the two classes, right? So it basically understands that each training instance or each training examples can belong to one of the two classes. So where the support vector machine during training builds a model that is capable to assign new data or the unseen data or a test data into one of the two classes, right? So after training, a support vector machine tries to build a model that can assign a new example to either one category or the other category. And this makes it a non-probabilistic binary linear classifier, right? So this is the most simplest case of an SVM. So we are treating this one as a binary linear classifier. So we will see later on that by adding some more features or having some advancements in the basic SVM, we can have also nonlinear classifier as well. The objective of applying support vector machines is to find the best line in two dimensions or the best hyperplane in more than two dimensions in order to help us separate our space in two classes. Now, the aim of a support vector machine is to draw a line which we call as a decision boundary if we are dealing in two-dimensional space. And if we go more from two-dimensional space to three-dimensional space, we can say that we want to have a hyperplane, which the purpose of both the line or a decision boundary and the hyperplane is the same, that we want to separate the instances belonging to different classes into their corresponding classes, right? So in two dimensions, we want to have a decision boundary, while in more than two-dimensional or three-dimensional space, we want to have a hyperplane which could distinguish between two sets of data and can classify different instances into their corresponding classes. The hyperplane or line is found through maximum margin. So this is basically the basic point of a support vector machine, that it tries to build the line or the hyperplane by using the maximum margin phenomena, which we discussed in last slide. It means that it maximizes the distance between data points of both the classes. So it tries to maximize the distance or maximize the margin between two different data points which are belonging to different classes or categories. So we can say that a support vector machine is a discriminative classifier formally defined by a separating hyperplane. And so we can define our support vector machine as a discriminative classifier, which tends to classify input dataset or training or and testing patterns into different classes through a hyperplane or a decision boundary. In other words, we can say that given labeled training data, because we are dealing under supervised learning domain, so we have some training data and we also have the labels of the training data. So once we have this labeled training data under supervised learning domain, the algorithm outputs an optimal hyperplane which categorizes new example. So what our algorithm is doing, it is trying to find an optimal hyperplane. So again, what does this mean here? This optimal hyperplane is it is that hyperplane which have the maximum margin between the instances and to itself, or the decision boundary. So we are basically categorizing new examples or test examples or new patterns into its corresponding classes or categories. In two-dimensional space, this hyperplane is a line. So as I told you earlier, that if we are in a two-dimensional space, this hyperplane will act as a line or a decision boundary, which I also showed you in the first figure. So this line divides a plane in two parts, where in each class lay in either side. So if we have two classes or we have a binary classification case, then these hyperplanes will divide the input space into two classes, and each class will belong to either, if it's a binary classification case, then one class can be 0 and other class can be 1. In the support vector machine algorithm, we plot each data item as a point in n-dimensional space, where n is the number of features you have, with the value of each feature being the value of a particular coordinate. So in an SVM algorithm, we have a set of data points, and those data points can be in an n-dimensional space. So I have told you that this dimensional space can be two-dimensional or three-dimensional, right? So it depends that how many features or we have, which we are basically plotting in an n-dimensional space. And for each feature, with the value of each feature, so each feature will have its corresponding value, and we basically plot it on the basis of its value on our particular coordinate system. Now once we have this n-dimensional plot, we perform classification by finding the hyperplane that differentiates the two classes very well. So the ultimate target or ultimate objective is to define a hyperplane, or to find a hyperplane which could basically differentiate this n-dimensional space into its corresponding classes. So these can be two or more classes in case of multi-class classification problem. Okay, so now let's go a little bit deeper in our support vector machine. So we have defined it very clearly, and now we know that what is a support vector machine and what is the ultimate target or objective of an SVM. Okay, now let's suppose that we have a label training set. So this is a training data set, and it has two classes, right? So now we are discussing the case in which we have a two-dimensional data set. So we have two different sets of data which belongs to two classes. To separate the two classes, there are so many possible options of hyperplanes that separates correctly. So if in the two-dimensional space, if I draw a hyperplane or a line or a decision boundary which could separate these two sets of classes, so I can have a number of hyperplanes which can do this task, right? So in order to classify two different sets of data, I can have one hyperplane, I can have two hyperplanes, I can have three hyperplanes, or maybe there are more possibilities of having more hyperplanes, and all those hyperplanes are basically successfully separating two sets of data. Now we can achieve exactly the same result using different hyperplanes, right? So we can have, for example, I have showed three hyperplanes here, which is L1, L2, L3, or maybe I can also have L4 hyperplane or L5 hyperplanes, and all these three or five hyperplanes are successfully achieving their desired goal. And what is the desired goal? The desired goal is to separate the two sets of data, right? So let's assume that all these hyperplanes can successfully separate the data sets correctly. However, if we add new data points, the consequences of using various hyperplanes will be very different in terms of classifying new data point into the right group of class, right? So now we say that, okay, our training data set was being correctly classified by all these hyperplanes, but what about if we are adding new data points in our data set, right? If we have some unseen data points, or we are constantly adding new data points in our data set, then the consequence of adding new data points can be different on each hyperplane. So maybe some hyperplanes will be able to distinguish or will be able to classify those new data points, or maybe there are some hyperplanes which are not being able to classify those new data points. So the addition of these new data points on the will be different on different hyperplanes in terms of classifying new data points, right? So some hyperplanes might be classifying new data points, and some hyperplanes might not be classifying those data points correctly.